Hi, hello everyone from Institute of Aeronautical Engineering. Myself, Dr. Purushotham Reddy. Today we are going to discuss about branch and bound general method and also 0-1 knapsack problem. The course objectives of this subject are design and analysis of algorithms are students will try to learn mathematical approach for analysis of algorithms, methods and techniques for analyzing the correctness and resource requirements of algorithms, different paradigms of algorithms design, including recursive algorithms, divide and conquer algorithms, dynamic programming, greedy algorithms, backtracking, branch and bound and graph algorithms. Strategies for solving problems not solvable in polynomial time. The course outcome with respect to the chapter branch and bound is after successful completion of this course, students will be able to utilize backtracking and branch and bound techniques to deal with traceable and untraceable problems. Next, branch and bound. The term branch and bound refers to all state space search methods in which all children of the E node are generated before any other live nodes can become the E node. We have already seen two graph search strategies, BFS and D search, in which the exploration of a cannot begin. New node cannot begin until the node currently being explored is fully explored. Both of these generalize to branch and bound strategies. In branch and bound terminology, a BFS like state space search will be called FIFO, first in, first out. Such the list of live nodes is a first in, first out list queue. A D search like state space search will be called LIFO, last in, first out such as the list of live nodes is a last in, first out list or stack. Now, here, first discussing about basics on this branch and bound. Now, here we see that backtracking method or technique, it is suitable for solving decision making problems. This backtracking technique, it gives optimal solution for decision problems. But this backtracking method is not suitable for finding optimal solution for optimization problems. So to overcome this drawback, we go this branch and bound technique. To overcome this problem, we introduce this branch and bound technique. In this branch and bound technique, here also we use the dead end method, but here we search the all different solutions. We search for all the different solutions, and finally we take the best solution as the optimal solution. Whereas in backtracking, if any solution is found, we stop the searching process. So that difference is there between this backtracking and a branch and bound. In this branch and bound, we solve the optimization problems by using three different strategies. One is that last in, first out strategy. This is depending on queue data structure. Next, this is first in, first out. First out strategy. It depends on queue data structure. The second one is last in, first out strategy. It's depending on stack data structure. Next, the third one is least cost search method. It depends on a ranking function. So here once again I repeating, this branch and bone technique, it is efficient method for solving optimization problems and find the optimal solution for the given optimization problems. Here we have three different types of strategies. The three different types of strategies are first in first out strategy, last in first out strategy, and LC search strategy. First in first out strategy, it is depending on queue data structure, whereas last in first out strategy depending on tag data structure. Least cost search technique, it is depending on ranking function. Next, here we come to first in first out strategy. This first in first out strategy depending on queue data structure. Now here we see that this is the first node. It has three childrens, 2, 3, 4. 2 has children 5, 6. 3 has children 7. 4 has children 8. This 5 has 9, 10. 6 has 11, and so on. Now here we see that first here in this FIFO strategy, first we enter the children of 1, that are 2, 3, and 4. So we eliminate 2 and we are expanding this live node. This E node as this is a low name now. This E node we are expanding now. That expanding nodes are 5 and 6. Now 3, 4, 5, and 6. Next we remove 3 and we are expanding the corresponding children, that is 7. Here we take that one. 4, 5, 6, 7. Now next 4 has children, so we are expanding that one. 5, 6, 7, 8. Next 5 is we expand this 5 children are 9, 10. 9, 10. Next we are expanding this sixth node. This children is 11. Next here you see that we removing this 7. It don't have any childrens. So remove this one. Similarly, we remove 8. This also don't have any childrens. Next remove 9. Next remove 10 and 11. So now here we see that among the solutions, which one is optimal solution? We choose that optimal solution. So in this way, we find the optimal solution by using first in first out strategy under this branch and bound technique. Next, similarly, here we see that next we come to last in first out strategy. This last in first out strategy, it depending on stack data structure. Stack data structure. Now here first here we expand this live node 1. The children are 2, 3, 4. Live node 1. The children are 2, 3, 4. We remove 2 and we insert the children of 2 that are 5, 6. Five and 6. Now we expand 6 that 6 or 5. So we expand 5. Now we write the children 4, 3, 6. Children are 9 and 10. This 9, 10 they don't have our children, so there is no chance to expand this one. We remove that one. Next we expand 6. 6 children is 11. 11 don't have any childs, so we remove that one. We expand 3. 7 don't have children, we remove that one. Next expand 4. The children is 8. 8 don't have children. Among these solutions, which one is optimal? We choose that optimal solution. So which one is best one? We choose that one as a optimal solution. So in this way, we find the optimal solution by using last in first out strategy. Next we come to that list cost search method, LC is search method, search strategy. In this LC search strategy, depending on ranking function. Now here you see that cost value is 1, cost value is 2, cost value is 3, cost value is 2, cost value is 4, cost value is 3, cost value is 5, cost value is 4, cost value is 3, cost value is 5. So now here we see that. First here we see that we expand 1. After expanding 1 has 3 children, 2, 3, 4. This one has cost function value is 1, this one has 2, this one is 3. Among this one is the minimum value, we choose this one. Next here we see that we're expanding 2, this cost function is 2, 5, 6, the children, 3, 7, 4, 8. Now here among this cost function, this one is 2, this is the minimum value, we can choose this one. Next we're expanding 5 and 6. Now here we see that this cost function value is 3. That means here we see that here among this is the least cost path value. So this is the optimum solution. This is the best solution with respect to the given problem. So this is the optimal solution. This is the optimal path for the given problem. So this one we find by using this least cost search strategy. So in this least cost search strategy, we find the least cost function C cap and upper bound using U. This is the lower bound, this is the upper bound. At any stage, this lower bound value is greater than this upper bound value. We kill the nodes, we kill that process, and we choose another path in that path to find the solution. And also here we see that here in this least cost strategy, here we choose among these cost functions, we choose the least cost value at the best one. So here we observe that C cap equal to 4, C cap equal to 3, C cap equal to 5. Among these least cost value is 2. So we choose that one. So in this way, we're defining that FIFO branch and bound method, LIFO last in first out branch and bound method, and the least cost search branch and bound method. Among these three, least cost search branch and bound method is the best one. It gives the optimal solution comparing with remaining two methods. And next, this is the control abstraction of branch and bound list search. Now here we see that procedure LC of T comma C cap. If T is an answer node, T means tree, C cap is the least cost function. If T is an answer node, then output T or return end if. E minus T, E is equal to T. E is equal to T means now first node is taken as E node. Initialize the list of live nodes to be empty. We're repeating this one for all the remaining nodes. Loop now repeating. For each child x of E, do if x is an answer node, then output the path from x to T and return end if. Call add of x. Call that add of x function. X is the new live node, and we're repeating for all the remaining nodes. Parent of x is equal to E. So in this way, we find the path from parent root node to child nodes. Repeat, if there are no more live nodes, then print that answer node and stop. End if. Call list of E. We call each time we call list cost value, and in that way we repeat that nodes, and we find the optimal path. So finally, here we repeat that one, and also finally print that list cost value and also list cost path value. Now, least cost method control abstraction. The search for an answer node can often be speeded by using an intelligent ranking function C cap for live nodes. The next E node is selected on the basis of this ranking function. Let T be a state space tree and C a cost function for the nodes in T. If X is a node in T, then C of X is the minimum cost of any answer node in the subtree with root X. Thus, C of T is the cost of the minimum cost answer node. The algorithm uses two subalgorithms, list of X and add of X, to respectively delete and add a live node from or to the list of live nodes. List of X finds a live node with the list cost function. This node is deleted from the list of live nodes and returned in variable X. Add of X add the new live node X to the list of live nodes. Procedure LC output the path from the answer node it finds to the root node T. Now we come to 0-1 knapsack problem using this branch and bound method. So first we come to knapsack. Knapsack means it is a bag. So in this bag we insert the weights up to maximum capacity of the bag. So here first that positive integers P1, P2 and so on, Pn are the profits, W1, W2 and so on, Wn are weight values, M is the capacity of the bag. Here we maximize the profit value, summation over I equal to 1 to n Pixi. Subject to W summation over I equal to 1 to n Wixi is less than or equal to M maximum capacity. So up to maximum capacity, we insert these weight values into the bag and also we maximize the profit value. That is the condition here. So now here in this branch and bound method, we convert this maximization problem into minimization problem. Simply we adding a minus before that summation. So minimize minus summation I equal to 1 to n Pixi. This is the minimization function. Now here in this 0-1 knapsack problem, here we see that suppose we insert the first weight into the bag, in that case x1 equal to 1. If you have not insert that weight value completely into the bag, in that case x1 value is 0. Similarly, x2 equal to 1. Suppose x1 equal to 1. Next here we get two different types of choices. One is x2 equal to 1 or x2 equal to 0. x2 equal to 1 means we insert that second weight value into the bag. If x2 equal to 0 means we are not inserting that weight value completely into the bag. Next, similarly here also x2 equal to 1 means we insert that second weight value completely into the bag. Otherwise, x2 value equal to 0 means we are not inserting that weight value into the bag. So the branch mechanism in the branch and bound strategy to solve this problem, 0-1 knapsack problem, in this way. Next, how to find the upper bound? By quickly finding a feasible solution in a greedy manner, starting from the smallest available, that is scanning toward the largest ice until M is exceeded. The upper bound can be calculated. How to find the ranking function? By relaxing our restriction from xi equal to 0 or 1 to 0 less than equal to xi less than equal to 1, knapsack problem, let minus summation over I equal to 1 to n Pixi be an optimal solution for 0-1 knapsack problem, and minus summation over I equal to 1 to n Pixi be an optimal solution for fractional problem. Let y equal to summation over I equal to 1 to n Pixi, y dash equal to minus summation over I equal to 1 to n Pixi. So y dash is less than or equivalent to y. How to expand the tree? By the best first such scheme, that is by expanding the node with the best lower bound. If two nodes have the same lower bounds, expand the node with lower upper bound. So in that way, we are expanding the tree. 0-1 knapsack problem using branch and bound technique. So procedure, upper bound of P means profit value, W means weight, M is maximum capacity, K is used for repetition function of these values. Now here we see that P, W, K and M have the same meaning in the algorithm. Wi and Pi are respectively the weight and profits in the ith object. Global W of 1 to n, we have n weights. P of 1 to n means we have n profits for integers I, k, n. Now B equal to P, C equal to W. For I equal to k plus 1 to n do. If C plus W of I are less than or equivalent to M, then C equal to C plus W of I, B equal to B minus P of I, N. Repeat and return finally that P value. N end upper bound value. So this is the function of U upper bound for knapsack problem. 0-1 knapsack problem example using a least cost branch and bound strategy. Now here consider the knapsack instance. N equal to 4 means it has only 4 instances. The corresponding profit values P1, P2 and so on. P3, P4 are 10, 10, 12, 18. Corresponding weight values W1, W2, W3, W4 are 2, 4, 6, 9 and maximum capacity M equal to 50. Now here we see that how to solve this problem here. Now here we see that profit values P1, P2, P3, P4, that values are 10, 10, 12, 18. Corresponding weight values W1, W2, W3, W4 that are 2, 4, 6, 9. Maximum capacity M equal to 50. First this one is the live E node. So first here we find lower bound and upper bound. Whenever we are going to find upper bound, we completely insert that values in the bag. That weight values completely insert into the bag. Now for example here we see, and also take in order 2 plus 4 plus 6, 6 plus 6, 12. Now here corresponding profit value 10 plus 10 plus 12. 32 minus 32. This one is the upper bound. Next, whenever we are going to calculate lower bound, we consider the fraction of some weight value that is also insert into the bag. And also we insert all these weight values up to maximum capacity. Now, here we see that 2 plus 4 plus 6, 12. 12 plus the 3 value we take from this 9. So 9 into 1, 3. 3 plus this 12, 15. So similarly, this 1/3 part we take from this weight value. 10 plus 10 plus 12, 32. Plus 18 into 1 by 3. 3 1 ja, 3 6 ja, 38. So this 38 is the least cost value, that is ranking function value C cap. So this is the value of C cap minus 38. Here we are using minimized function. That's why we write minus. Next, now we are expanding this one. Here x1 equal to 1, x1 equal to 0. x1 equal to 1, x1 equal to 0 means x1 equal to 1 means the weight 1, W1 we consider. x1 equal to 0 means W1 weight, W1 is not considered to insert into the bag. Now here we consider means 2 plus 4 plus 6, 12. Same 10 plus 10 plus 10, 12. 32 minus 32 is the lower bound, upper bound. Same here also 2 plus 4 plus 6 plus 9. In this 9 we take 1/3 part. So here also in this 18 we take 1/3 part. 6 plus 32 minus 38. This is the lower bound or ranking function value. Next here also, now x1 equal to 0 means we are not consider weight W1. If we are not consider weight W1 means we are not consider this weight W1 2 we are not consider. Now 4 plus 6 10. 10 these two only we consider. Now 10 plus 12 22 minus 22 is the upper bound. This is the upper bound. Next here we find lower bound. 4 plus 6 10. 10 here from this one we take 5. So we multiply 9 with 5 by 9. Now here also Here also we consider, we take 5 by 9 part of this 18. 10 plus 12, 22 plus 18 into 5 by 9. 9 1 ja, 9 2 ja. 2 5 ja, 10 plus 22, 32. 32 is the lower bound. Now here we see that in this level, so already we expanded this 2. In this level, which one is minimum? We choose that one. So minus 38, minus 32. Among this list functions, minus 38 is the minimum value. So we choose this one. So that means this is the least path now, up to now. So now E2 is the E node. Now we are going to expand this one. Now here two cases arise, x2 equal to 1, x2 equal to 0. Already we choose x1. So x2 means second weight. x2 equal to 1 means we completely insert the value x2, x2 value completely into the back. Next, x2 equal to 0 means we are not inserting completely that second weight into the back. So now x2 equal to 1, x2 equal to 0. Now x2 equal to 1. Now here we considering this 2 value. Already x1 equal to 1 means compulsory we consider the first value. x2 equal to 1 means this 4 also we consider. 2 plus 4, 6, 6 plus 6, 12. Corresponding profit values 10 plus 10 plus 12, 32. Minus 32 is the upper bound value. So next, lower bound value. Lower bound means when we are going to calculate lower bound, we consider fractional values also. So 2 plus 4, 6, 6 plus 6, 12 plus in this 9, we take 1/3 part. So 9 into 1 by 3 value. 3 plus 12, 15. 15 equal to this maximum capacity. Here also from this 18, we take 1/3 part. So 18 into 1/3, 6. This 6 added to this one, 10 plus 10, 12, 20 plus 12, 32 plus 6, 38. Minus 38 is the lower bound. Here x2 equal to 0 means we are not consider the second weight value. So now 2 plus 6, 8. 8 plus remaining 7 value, here 8. 8 plus 9, 17. It is more than 15. So we consider only 2 plus 6, 8. 10 plus 12, 22. 22 is the upper bound value. Now we find lower bound value. 2 plus 6, 8. 8. From this 7 will take 9 will take 7 value. 8 plus 7, 15. That is equal to maximum capacity. So this 9 get cancelled here 7. 7 plus 2 plus 6, 8. 8 plus 7, 15. This is equal to maximum capacity. From this 18 also we will take 7 by 9 value. 7 by 9. 9 1 ja, 9 2 ja. 2 7 ja, 14. This 14 is added to this values. 10 plus 12, 22 plus 14, minus 36. Minus 36 is the lower bound value. Now here we see that in this lower bound minus 38, minus 36, least value is minus 38. So we choose this one, x2 equal to 1. That means x1 we consider already. Now x1 is already considered. Now x2 is considered. Now x1, x2, these two are considered. Now here we see that next now 4 is the live node or E node. Now we are going to expand this. Now x1, x2 completed. Now we come to x3 means third weight. If x3 equal to 1 means we insert completely third weight into the back. x3 equal to 0 means we are not considered to insert that value into the back. Now here we see that already x1, x2 are considered. Now x3 also consider means 2 plus 4, 6, 6 plus 6, 12. Corresponding, so 12 is less than 15. So there is no problem to insert all these three values. x4 12 plus 9, 21 more than 15. So we are not inserting completely this fourth value. So now corresponding value 10 plus 10 plus 12 minus 32. Minus 32 is the upper bound. When we are going to calculate lower bound values, compulsory we consider fraction of weight values. So 2 plus 4, 6, 6 plus 6, 12, 12 plus in this 9 will take 1/3 part. 12 plus 3, 15. So here in this 18 also will take 1/3 part. 6, 10 plus 10, 20 plus 12 plus 6, 38. Minus 38 is the lower bound value. Now here x3 equal to 0 means we are not consider third weight value. We consider first two weights. 2 plus 4, 6, 6 plus 9, 15, 15 equal to this maximum capacity 15. So now 10 plus 12, 22 plus 18, okay. 10 plus 10, 20, 20 plus 18, minus 38. Minus 38 is the upper bound. In second case also 2 plus 4, 6, 6 plus 9, 15, that one is completely filled. Then no need to take any other fractional value. So here also in this case also 10 plus 10, 20 plus 18, minus 38 is the least cost value or least lower bound value. Now here we see that among this, here lower bound value is minus 38. Here lower bound value is minus 38. Both are equal. Whenever lower bounds are equal at any level, any two lower bounds are equal at any level, so we check the upper bound values. Here upper bound value is minus 32. Here upper bound value is minus 38. So among these two, least value is minus 38. So now we see we take this one. So we take this x3 equal to 0. So we won't take this x3 equal to 1. Now here we see that now naive node is 7 or E node is 7. Now we are going to expand this 7. Now here also two cases arise. One is x4 equal to 1, another one is x4 equal to 0. Now x4 equal to 1 means we consider fourth value. So already we consider x1, x2, x3 is not considered. Next we consider x4. So x3 is not considered means this W3 weight is not considered. We consider 2 plus 4, 6 plus 9, 15. The corresponding profit values are 10, 10, 18. 10 plus 18 is 38. 10 plus 10 plus 18 is 38. So that minus 38 is the upper bound here. Similarly, here we see that whenever we are going to calculate lower bound, in that case also we consider only this x3, W3 value is not, we are not considered. So 2 plus 4, 6, 6 plus 9, 18, 15. So that is equal to m value. Now here also 10 plus x3 is not considered, 18, 38. Minus 38 is the lower bound. Next, x4 equal to 0. x4 equal to 0 means we consider x1 here already, x2, x3 is not considered, x4 also not considered. That means x3, x4, these both are not considered. This both are not considered means here also these two are not considered. So only these two are, we are going to consider only these two. So 10 plus 10, 20. So 10 plus 10, 20. This 20 is the upper bound value. Similarly, here we are going to calculate lower bound value. In that case also here we observe that here we consider only this W1 weight value 2, W2 weight value is 4. 2 plus 4 is 6. 6 is less than 15 than the maximum weight value. Now here we see that here also consider the corresponding profit values 10, 10. 10 plus 10 is 20. 20 is the lower bound value. Now here we see that here lower bound value is minus 38. Here lower bound value is minus 20. Among these values, which one is minimum? Minus 38 is the minimum. So we consider this value x4 equal to 1. And also here observe that lower bound, upper bound, both values are equal, and also here already all that 4 instances are completed. So we stop here. So in this way, we find this optimal solution by using this LC branch and bound method for the 0-1 knapsack problem. Now here we see that Here the solution path is x1 equal to 1, x2 equal to 1, x3 equal to 0, x4 equal to 1. And the corresponding weight values are w1 summation I equal to 1 to n wi xi equal to 2 plus 4 plus 0 plus 9, 2 plus 4, 6, 6 plus 9, 50. This also write it as 2 into x1 value 1, 4 into x2 value is 1, 6 into x3 value is 0, 9 into x4 value is 1, total value is 50. Now maximize profit value summation I equal to 1 to n pi xi is equal to p1 x1 plus p2 x2 plus p3 x3 plus p4 x4. So p1 value is 10, 10 into x1 value is 1, p2 value is 10 into x2 value is 1, p3 value is 12 into x3 value is 0, p4 value is 18 into x4 value is 1. 10 into 1 is 10, plus 10 into 1 is 10, plus 12 into 0 is 0, plus 1 into 18 is 18, which is equal to 38. So the maximum profit value is 38, and the corresponding weight value is 15, which is equal to maximum weight value m. Maximum capacity of the bag is m. So here the maximum profit value of the 0-1 knapsack problem is 38. This 38 we find this maximum profit value we find by using this LC branch and bound, and also the solution path or the solution constraints are x1 equal to 1, x2 equal to 1, x3 equal to 0, x4 equal to 1. Now here once again, here I am repeating this one. Now here we see that the procedure once again I am repeating that one. First here 4 instances are given, n equal to 4. The corresponding profit values are given P1, P2, P3, P4. That values are 10, 10, 12, 18. 10, 10, 12, 18. Next, the corresponding weight values are given 2, 4, 6, 9. The maximum capacity value is given 15. Here, in this knapsack problem, we insert the weight values up to maximum capacity 15. That is the meaning of that one. First here, this node 1, this is the root node, this is the E node. First we are going to expand that one. First to find lower bound, upper bound of this node. So whenever we are calculate upper bound, we completely insert the weight values into the bag. That's why here we completely insert these values 2, 4, 6. 2 plus 4, 6, 6 plus 6, 12, 12 is less than 15. Suppose we have 9, it is more than the 15 we get. So the corresponding profit value is 10 plus 10 plus 12 minus 32. Minus 32 is the upper bound. Whenever we are going to calculate lower bound value, we are consider the fraction of weight values. That values also insert into the bag. So 2 plus 4 plus 6, 12 plus that 1/3 part we will take from this 9, that is 3, 3 plus 12, 15. 15 equal to maximum profit value 15. Now 10 plus 10 plus 12, 32. Here 1/3 value of this 18 is 6. 32 plus 6 is 38. 38 is the lower bound value. Now this is the E node. Now we expand this one. Now we expand this one. This here we get two cases arises, x1 equal to 1, x1 equal to 0. x1 equal to 1 means we insert that weight value into the bag. If x1 equal to 0 means we are not inserting that weight value into the bag. Now here x1 equal to 1, so we insert that weight value into the bag. So in this case x1 equal to insert into the bag means we consider w1 value 2 plus 4 plus 6, 12. The corresponding profit value is 10 plus 10 plus 12, 32 minus 32 we get upper bound. Lower bound is whenever we are going to calculate lower bound, compulsory here we take the fraction values of weight values. So now here 2 plus 4 plus 6 plus 1/3 part of 9. Here also 10 plus 10 plus 12, 32 into 1/3 part of this 18 is 6, minus 38 is the upper bound. Similarly, here we calculate x1 equal to 0. At that time, we calculate lower bound and upper bound values. Here, x1 equal to 0 means we are not consider that first weight value. So, we consider 4 plus 6, 10, 10 plus 12, 22, minus 22 is the upper bound. Lower bound is we consider the fractional part. So, now here 4 plus 6, 10, remaining 5 value will take from this one. So, multiply with 5 by 9. So, here also 18 into 5 by 9, that value is 40 or 10. That value here we take, that value is minus 32 here we get. Similarly, next year among these values, in this lower bound value is minus 38, here lower bound value is minus 32. Among these values, least value is minus 38. So we consider this value minus 38. So now now this is the E node. Now we expand this one. Now here also two cases arises, x2 equal to 1 and x2 equal to 0. Now x2 equal to 1, x2 equal to 0. Here x2 equal to 1 means here we consider this weight value completely into the bag. W2 weight value completely into the bag. If x2 equal to 0 means W2 weight value is not considered completely into the bag. Now here we consider this value first. Here we consider already we consider W1 weight value. Next we consider W2 weight value. 2 plus 4, 6, 6 plus 6, 12, 10 plus 10 plus 12, minus 32 is the, here minus 32 is the lower bound, upper bound, minus 38. So we consider fractional part, we get minus 38 is the least bound or lower bound. So now here, similarly here also, x2 equal to 0 means we are not consider W2 weight value. W2 weight value 4 is not considered. 2 plus 4, 2 plus 6, 8, 10 plus 12, minus 22. Minus 22 is the upper bound. Whenever we are going to calculate lower bound value, we consider fractional part. So 2 plus 4, 6, remaining here 2 plus 4, 6, 8, 8 and remaining 7 value we take from this 9. So multiply this 9 with 7 by 9. Here also 18 with 7 by 9 we get 14. 14 plus 22 minus 36 is the lower bound. And now we compare these lower bounds, minus 38, minus 36. Among this, minus 38 is the least value. So now we are going to expand this one. So already x1 consider, w1 consider, x2 equal to 1 means w2 consider. Now x3 equal to, here two cases arises, x3 equal to 1, x3 equal to 0. So now x3 equal to 1 means we consider third weight value. x3 equal to 0 means we are not consider third weight value. So if you consider third weight value, 2 plus 4, 6, 6 plus 6, 12, 10 plus 10 plus 12, minus 32 is the upper bound value. Lower bound is, whenever we are going to calculate lower bound value, we take the fractional part of weight value. So 2 plus 4, 6, 6 plus 6, 12. So 1/3 value we take from this 9. So here also we take 1/3 value. 6. 6 plus 32 minus 38 is the least bound or lower bound. Now similarly, here we are going x3 equal to 0. x3 equal to 0 means here we see that that the third weight value we are not considered. 2 plus 4, 6, 6 plus 9, 15. 15 is equal to m value. So now here 10 plus 10 plus 10, 20. 20 plus 18, 38 is the lower bound value and also upper bound value. Here that weight value is equivalent to maximum capacity value. So this lower bound and upper bound values both are same. So this value are equal here. Now here we see that we compare this C cap values. Here minus 38, here also minus 38. So lower bounds values are equal. Whenever lower bounds values are equal, and now we compare upper bound values. Here upper bound value is minus 38, here upper bound value is minus 32, here minus 38. Among these two values, minimum value is minus 38. So now we are going to expand this minus 38, this value. So we expand this one. So now here two cases arises. One is x4 equal to 1, another one is x4 equal to 0. x4 equal to 1 means we consider fourth weight value. Already we are not consider third weight value. x1 equal to 1, x2 equal to 1, x3 equal to 0. So x4, 2 plus 4, 6, 6 plus 9, 15, 10 plus 10, 20, 20 plus 18, 38. Minus 38 is the lower bound value. Minus 38 is the upper bound value. In both cases, here we get that maximum value, maximum capacity value 15. So in both cases we get minus 38. Next, similarly, Here x4 equal to 0. X4 equal to 0 means we are not considering this x4. Already x3 is not considered. 2 plus 4, 6, 10 plus 10, 20. 20 is the lower bound, 20 is the upper bound for this given problem. Now among these values minus 38, minus 20, least value is minus 38. So we choose this path. So already all four constraints completed. So we stop here the searching process, and also this is the optimal solution. That optimal solution is x1 equal to 1, x2 equal to 1, x3 equal to 0, and x4 equal to 1. The corresponding maximum weight value is so 2 into 1 plus 4 into 1 plus 6 into 0 plus 9 into 1. That means W1 into x1, W2 into x2 plus W3 into x3 plus W4 into x4. That value is 15, which is equal to maximum capacity value. So the maximized profit value is summation or I equal to 1 to n pi xi. So P1 x1 plus P2 x2 plus P3 x3 plus P4 x4. P1 value is 10 into 1 plus x1 value plus 10 into x2 value is 1, 10 into 12 into x3 value is 0 plus 18 into x4 value is 1, 10 plus 10, 20, 20 plus 18, 38 minus this 38 is the maximum profit. So maximum profit of this 0-1 abstract problem is 38. The corresponding solution is solution path is x1 equal to 1, x2 equal to 1, x3 equal to 0, x4 equal to 1. So in this way, we solve the 0-1 abstract problem by using least cost branch and bound method. Thanks to everyone.
Like, share and subscribe. Hit the bell icon for more updates.